Hello everyone. In this video, I would like to look at this kind of exam question with the modulus function, because in my experience, students often find various aspects of this particular question quite confusing. So let's have a look at question 11. It says, figure 2 shows a sketch of a graph with the equation y is equal to 2 times the modulus of x add 4 minus 5. The vertex of the graph is at the point P as shown in figure 2. Find the coordinates of P. Now, very often, students really have no idea what to do about this. But what I would say is when you've got y is equal to a times the modulus of x add b add c, like that, it's very analogous to this form of completing the square. Okay, so it's not the same thing, but it is. But just put a little box around the bubble around that. It's very, I'll put CF for compare with. Okay, now we know from this type of form of a quadratic equation that the turning point is given by the coordinate minus BC. Okay, and it's very similar here. We have that the vertex is also given by the coordinate minus BC. So it works in the same way as finding the turning point in completing the square. Okay, so applying that idea to part A, we can see that the coordinates of the vertex are in fact going to be minus 4, minus 5. Okay, so that's how you approach that, which again, in my experience, a lot of students are unclear in their own mind about that. So that's part A done. Now, part B, solve the equation. Again, there are various approaches to this particular part of the question, but the one that I prefer is just to solve it once with the modulus function as being positive and solve it once with the modulus function as being negative. Because if you remember way back when earlier in the course, when we were defining the modulus function, we said that what the modulus function did is it was a special function that kept something that is positive as positive, and yet if something's negative, it makes it go positive. And the way it did that in the definition of the function was by putting a minus in front of it. That's why it works. So all of that to say, let's solve it first of all with it positive. So we're going to have 3x add 40 is equal to 2 x add 4 minus 5. So we've got 3x add 40 is equal to 2x add 8 minus 5. So we're going to work this out. So we've got 3x add 40 is equal to 2x add 3. Okay, and then we're going to have that x is equal to minus 37. Okay, so that's one of our solutions. And now we're going to solve it with a minus in front. So let's 3x add 40 is equal to 2 times. I'm going to put it in brackets just to emphasize the fact that what's happened is that the minus has been put in front of that bracket. Okay, so that's why I'm kind of like putting it in that kind of format. But now in the next line, I'll just write it as 3x add 40 is equal to minus 2 open brackets x add 4 like that minus 5. Okay, but I did it that way just to emphasize that what the modulus function is doing is put a minus in front of that bracket. Okay, sometimes if you don't represent it in that right way, you can make an error. So let's now expand this. So we've got minus 2x, and we're going to have this time minus 8 minus 5. So minus 13 minus 2x is equal to 3x add 40. So now we're going to have 5x is equal to minus 53. Yeah, 5x is equal to minus 53. So therefore x is now equal to minus 53 over 5. Minus 53 over 5. Okay, so we've got our two different solutions there. Now 53 over 5, let's just see what that is as a decimal. 53/5 is minus 10.6. So x is equal to minus 10.6. Okay, that's good. Now we've got to think about, so there we go, that's that solved. Now we've got to think about, can we actually have both of those solutions or not? And I think if we were to represent the line y equals 3x add 40 on our sketch, let's just do that now. Okay, so if I was to annotate here and represent it on the sketch. So I'm just drawing a line that sort of like roughly represents our 3x add 40. So let's just say it's something like that. Make sure it's steeper than that one. This has a gradient here of 2, so I've just represented that as being a steeper gradient there. And so you can see from that we've actually got just this one point of intersection here. So we've only got one point of intersection there, like that, okay? We haven't actually got 2 points of intersection. So we need to decide which one of those makes sense as our answer. And I think hopefully we can see that this is the one that we don't need and that this is the appropriate one. I mean, this is the one that makes sense when we think that the coordinate of our vertex here is -4, -5. And the line, the point where we've got intersecting is not that far to the right of the vertex. So it makes sense that the solution is going to be -10, -6, and not in fact the one that is -37, which would be like somewhere over here. I hope that makes sense. So we've ruled out one of the solutions. We just need the one because of the way that the straight line was on there. Okay, that's part B done. Now, oh my goodness, this part C, wow. This is the bit that is the most confusing. As I say, that first bit with the vertex confuses people. And this bit, in my experience, almost universally confuses people. So I think this will be hopefully this will be quite valuable to everybody. So we've got 0, we've got y, we've got x. Now, the line L has the equation y is equal to ax. Now I'm going to illustrate this with the aid of a ruler, which I have here. Okay, the line L is equal to y equals ax, where a is a constant. Given that the line L intersects the curve at least once, find the range of possible values of a. Okay, writing your answer in set notation. Now, the mark scheme doesn't give much away here. It just kind of like writes down what the answers are. So it is useful to have a discussion about where this comes from, I think. So first of all, we know that our line y equals ax. I'm going to try and represent it. If you can imagine, we're viewing it from above. Okay, so there's our line y equals ax. Notice it's going through the origin, okay, because there's no y-intercept. And in this first scenario where I'm holding the ruler now, the line is parallel to the curve, okay? And we know, well, we can infer from the equation of the curve that the gradient here is 2, okay? So the gradient of this line is 2. And that's come from, like, again, it's very analogous to like the completing the square form. Okay, so we've got like, it's analogous to y equals mx plus c, to be honest. So we've got, this is a gradient of 2. Okay, so this, we have no point of intersection when the equation y equals ax is of the form y is equal to 2x. If y equals 2x, we've got no points of intersection whatsoever, okay? Because these two lines run parallel and the curves don't cut at all. Now, the question's asking us, where do they intersect at least once? So if the gradient is just a little bit bigger than 2, then you can see, look, that the curves are intersecting, they're intersecting there, and there's one point of intersection. So they're going to start to intersect when the value of a is greater than 2, okay? So we've established we're going to get at least one point of intersection when the gradient of a is bigger than 2. So let's examine what happens. So the gradient is bigger than 2. We've now got a point of intersection. Okay, and all the way around, we've still got one point of intersection. The curves are still crossing once all the way around as a gets bigger and bigger and bigger. In fact, at this point here, it's intersecting twice now. Okay, so it's intersecting twice, bigger, 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 intersecting, intersecting, intersecting all the way around. And it continues to intersect all the way around. We've still got 2 points of intersection, and it intersects all the way around up until we get to the point where the ruler is just here touching this vertex here, okay? So we're continuing to have points of intersection at this bit here. Now let's think about this, okay? So this is where we have back to having one point of intersection, and we need to think about where on earth is this point. Well, we said earlier in the question that the vertex of this point had coordinates, let's write it on, -4, -5, okay? So -4, -5. So actually, let's represent that on our graph like that. So we've got -4 along the x, and we've got -5 down the y. So the gradient, being rise over run, is going to be like -5 over -4. In other words, the gradient here is 5 over 4. The gradient is equal to 1.25, okay? So that means this is where we have y is equal to 1.25. I've written m there, I should have written x. The equation of the line is y equals 1.25x. Okay, in our form y equals ax. So there, that is where it stops. So let's think about what that is. So if we have a gradient of 1.25, then we have one point of intersection, okay, which is at the vertex. And if the gradient becomes less than 1.25, then we're back into that zone of where we've got more than one solution. So what we're saying is that A has to be less than 1.25. Okay, let's just examine that again. So if we have a gradient of exactly 2, we have no points of intersection at all because they run parallel to each other. As soon as the gradient goes a little bit bigger, we start to intersect, okay? And that intersection carries on all the way around as the gradient changes all the way around, up until we get to this point here, at which point there is only one solution again, where it's at the vertex. And if the gradient gets any steeper than that, there's no solutions again. And this point corresponds to a gradient of 1.25. And as soon as the gradient is less than 1.25, we're back into our intersections again. Okay, so that's why the range of values where there are no intersections are these ones here. But the question's asking us, what's the range of values where there is at least one intersection? So it's when A is greater than 2, okay, and it's when A is less than 1.25. So let's write that down. A has to be greater than 2. Wrong. A has to be greater than 2. Or A has to be less than 1.25. And it asks us to represent this in set notation. So using set notation, let's use the old curly brackets. So A is a member of the set of the elements of A is less than 1.25. And because it's or, we use the symbol union, okay? So we're basically saying that A is a member of the set of A is less than 1.25, or A is a member of the set where it is greater than 2. And that is our answer written in set notation. And I hope that explanation clears that up, because I know from previous experience that students almost universally find that particular type of question quite challenging. I hope you found that helpful, and I will see you in the next video.